A very good morning to all of you. So today we are going to start our next chapter of inorganic chemistry, that is P block elements. Okay, so we are done with the S block elements. Now we are moving to P block elements. Now what are P block elements? So as in case of S block elements, so S block elements are those in which the last electron enters the S orbital. Okay, so similarly P block elements are those in which the elements in which last electron enters any of the four any of the three p orbitals. Okay, so the elements in which the last electron enters any of the three p orbital is known as p block elements. So now as we all know, there are three orbitals of p block. Okay, there are three p orbitals and we all know that there are two electrons in each orbital, so there are 3 into 2 6 electrons possible. Okay, so it means there are 6 groups involving the p block. Okay, and the groups are from group number 13 to group number 18. Okay, so group number 13 to group number 18 elements except helium. Okay, except helium are termed as p block element. Okay, are termed as p block element. Now uh, now what are group number 13, group number 14, 15, 16, 17 and 18 elements? So group number 13 is of boron family. Okay, group number 13 is boron family. So boron, aluminium, and then we have germanium. Okay, then we have germanium and boron, aluminium, then we have gallium, indium and thallium. Okay, group number 13. And then we have group number 14, that is carbon family, carbon, silicon, germanium, tin, and then we have lead. Okay, so this is group number 14. And then we have group number 15, nitrogen family, nitrogen, phosphorus, arsenic, antimony, and then we have bismuth. Okay, and group number 16 is oxygen family, oxygen, sulfur, selenium, tellurium, polonium. Okay, and then we have group number 17, which is halogen family. Fluorine is the first member, chlorine, bromine, iodine. Okay, this is radioactive. Group number 18 is we have argon, neon, argon, krypton, xenon, and then we have radon. Okay, so these are the 6 groups of p block. Okay, so the main thing is that these all groups contain both metal, non-metal as well as metalloids. Okay, so all are contained. Now what is the general configuration? So general configuration electronic configuration. So the general electronic configuration is Ns from 1 to 2 and Np from 1 to 6. okay, and n, the value of n is from 2 to 7, okay. How it is from 2 to 7? Because all these elements are in 2p orbital, okay. These are in 3p, 4p, 5p, 6p, and then we have 7p, which are radioactive in nature, okay. So that is why in boron the last electron is in 2p. In carbon, nitrogen, oxygen, fluorine, and neon, the last electron enters the 2p, okay. So similarly in aluminium 3p may, and then in gallium 4p, and then indium may 5p. These all have their last electron in 4p. These all have their last electron in 5p, and these all have their last electron in 6p, okay. So this is all about their electronic configuration. So it has 2 electrons in the p orbital. इसके पास 3 हैं, इसके पास 4, इसके पास 5, and then it has 6 electrons, okay. तो कुछ इस तरह से ट्रेंड चलता है हमारे पास. Now let us talk about their oxidation state. So the oxidation state, the highest oxidation state is shown by these uh, these elements is derived from their group number, okay. So the highest oxygen state is group number -10, okay. So the highest oxygen state is group number, can be easily predicted by group number -10. So as boron is in group number 13, so boron family's highest oxygen state is 13 minus 10, that is equal to +3, okay. Similarly for carbon, that is +4. For nitrogen +5. For oxygen the highest oxygen state is +6, or it may be minus also, -2 is also shown by oxygen family. Similarly for fluorine the highest oxygen state is +7, okay. So for these all elements the highest oxygen state is +8, but only xenon is able to show the state, okay. So now let us discuss about the oxygen state of each and every group one by one. So for boron, if we talk about boron, so boron shows oxidation state of +3 only, okay. So it is able to show oxygen state of +3. Similarly aluminium is also able to show only +3 oxygen state. And if we move further to gallium, indium, and thallium, so gallium can also show, they have a tendency to show oxygen state which is 2 number less than their group oxidation state, okay. So that state which is related to their group is known as group oxidation state, okay. So this is known as group number -10 is known as group oxidation state, which is derived from their group oxidation state, okay, or group oxidation number, GON, group oxidation number, or GOS, group oxidation state, okay. Now if we talk about gallium, indium, and thallium, then they have a tendency to show +3 as well as +1. Now what is the reason why they are showing +1? That is due to inert pair effect, okay. We have already learnt in this effect in our third chapter, that is periodic properties. So inert pair effect is that effect in which s orbital doesn't take part in the bonding. That is why its 2 electron will not take part, and the oxidation state decreases from by 2 units, okay. Like here it is decreased from +3 to +1, okay. So as we move from top to bottom, the tendency to show inert pair effect increases, so the stability of lower oxidation state increases, okay. So write it in a notebook, this thing also, that as we move from top to bottom, the tendency to show lower oxidation state increases because of the increase in the tendency of inert pair effect, okay. So these three have a stable oxygen state of +3 and +1. If we talk about thallium and indium, they show +1 as a major oxygen state, okay. +3 is not shown by these elements. Now let us talk about carbon. So carbon have a tendency to show +4 as well as -4. Okay, so carbon have a tendency to show +4 as well as -4. And if we talk about silicon, so silicon have a tendency to show +4 only. Okay, it has a tendency to show +4. Now if we talk about germanium, germanium, tin and lead, so they have a tendency to show both +4 as well as +2. Okay, so they have a tendency to show, they all have a tendency to show +4 as well as +2. But for lead as well as tin, the +2 oxygen state is more stable than that of +4 due to inert pair effect. Now let's move on to the next family. So if we talk about sodium, that is nitrogen. Okay, so nitrogen has a tendency to show oxygen state of from +3 to from +5 to -3. Okay, so it has a great tendency, has a higher tendency to show variable oxygen state from +5 to -3. So compounds of nitrogen exist in oxygen state from +5 to -3. -3 uh, with the higher electronegative element, like in case of NF3. Okay, NF3 it is +3. Okay, and if it is combined with the lower electronegative element like NH3 may, so here nitrogen have a oxygen state of -3. Okay, and hydrogen is of +1. Okay, similarly if we talk about N2O5, so in N2O5 nitrogen is in +5. Okay, similarly in N2O3 it is in +3. So it has a variable, it has a very high tendency to show variable oxygen state. Now if we talk about phosphorus, so phosphorus have a tendency to show -3, +3 and minus I think +5 also. Okay, so it has a tendency to show -3, +3 as well as +5. And if we talk about the other elements, so similarly arsenic also have a tendency to show -3, +3 and +5, and the rest of the two elements have a tendency to show +3 as well as +5. So one more thing you have to keep in your mind, that as we all know, on going from top to bottom, the electropositivity increases. Okay, electropositivity increases, in it means they have the tendency to show negative oxygen state decreases. Okay, so write it in a notebook, this thing also, that as we move from top to bottom, the tendency to show negative oxygen state decreases और tendency to show positive oxygen state increases. उसमें भी कौन से वाली? Lower. Okay, due to inert pair effect. So these things you have to keep in your mind, that as we move from top to bottom, electropositive character increases, metallic character increases. That is why they have a tendency to form cation, not anion. Okay, and cation is of lower oxygen state, that is due to inert pair effect. So there are 4 or 5 concepts okay, combined with each other in order to explain the effect of oxidation number. Okay, why the oxidation number is decreasing. Now let's move on to the other three elements, other three group elements. So for oxygen, the higher oxygen state is +2, and then they are not able to show the group oxidation number because of the lack of d orbitals. Okay, I will explain it to you later, that all the first elements have a different behavior than that of the other group elements. Okay, so the first member of all the group elements have a different behavior than that of the rest of the elements. So oxygen is able to show +2, -2, +1 and -1. Okay, so it is able to show +2, +1, -2 and -1. And if we talk about sulfur, selenium and tellurium, they have a tendency to show -2, +2, +4 and +6. Okay, so they all have a tendency to show -2. Not in case of tellurium and polonium, so they don't have a tendency to show minus oxygen state, but sulfur and selenium have a tendency to show -2, uh, +2, +4 and +6. And if we talk about tellurium and polonium, they have a tendency to show +4 and +6 only, in which +4 is more stable due to inert pair effect. Similarly, if we talk about group number 17 elements, so fluorine have a tendency to show -1 only, okay, and chlorine have a tendency to show -1 and +1, +3, okay. So it has a tendency to show +1, +3, uh, +5, +7 also, okay. So they all have a tendency to show, only chlorine have a tendency to show -1. All others also show -1, but in very less compounds, okay. They have a tendency to show positive oxygen state because of higher electropositivity, so or low electronegativity, okay. So these are the stable oxygen state of these elements. Now if we talk about neon, argon, krypton, xenon. So the oxidation number for these two elements is 0 because they don't take part in bonding, because they are very stable and their electronegativity is, or you can say, their orbit, the ionization energy for these two elements is very high, okay. And if we talk about krypton, so krypton have a tendency to show +2 as well as +4 oxygen state, okay. It doesn't show higher oxygen state, +2 as well as +4 only. And if we talk about xenon, so xenon compounds exist in +2, +4, +6 and even in +8 also, okay. It has a tendency to show +2, +4, +6 and +8, okay. And radon is, as we all know, it is radioactive in nature. Now let us talk about their nature. So there is a borderline, okay. There is a borderline in between these all elements. There is a borderline. Now what is that borderline? Let us discuss about that one also. So there is a change in the properties due to this borderline, okay. So let me rub it off. Okay, so now these are the elements. Now if we talk about their nature, okay, out of these, which element is metal and which is non-metal. So there is a borderline, here is a borderline, that boron, silicon, uh, similarly we have germanium, arsenic, antimony, okay, antimony, and then we have tellurium, okay, tellurium and polonium. So these all elements which are in block are metalloids, okay. So these all elements are metalloids, and the rest of the elements, okay, if we talk about these all elements, so these are metals which are in circle, okay. These all are metals, these all are metals, and rest of the elements, okay, rest of the elements are non-metals. These all elements which are in triangle, these all are non-metals, okay. So a P block contain both metal, non-metal as well as metalloids, okay. So these all are non-metals which are in triangle. So as we move from left to right, there is a sudden change in the properties due to this borderline, okay, due to this borderline, because we are moving from metal to non-metal. So how can we check their nature? By making their oxides, okay, by comparing the nature of their oxides. So metal oxides are always basic in nature, okay. So write it in a notebook that metal oxides are always basic in nature. Okay, basic in nature. And if we talk about the non-metal oxides, so non-metal oxides are acidic as well as neutral in nature. Okay, because water, as we all know, is neutral. Similarly, CO, carbon monoxide, is neutral. So so the non-metallic oxides are acidic as well as neutral. Okay, one more thing you have to keep in your mind, that as the electropositivity of metal increases, okay, as their ionization energy decreases, their basic character increases. Okay, so as we move from top to bottom, their electropositivity increases, it means their uh, basic nature increases. And for non-metal, as we move from uh, top to bottom, or as we move from top to bottom, their tendency to show acidic character decreases. Okay, because as we move from top to bottom, metallic character increases. And as we move from left to right, okay, as their electronegativity increases, their tendency to show acidic character increases. Okay, they are more acidic. And one more thing, as the oxidation number increases, like in case of nitrogen, so nitrogen have a tendency to show oxidation state from -3 to +5. Okay, so if we compare the two compounds, their acidic nature, if we compare N2O3 with N2O5, which is more acidic? So N2O5 is more acidic because its oxidation number of nitrogen in N2O5 is +5, and in N2O3 it is +3. So higher the oxidation number, higher will be the acidic character. Okay, so this thing you have to keep in your mind, that all the non-metals have a tendency to show acidic as well as neutral nature, and all the metals have a tendency to show basic nature. Okay, so this is the main difference between the properties. Okay, and if we talk about the oxides of metalloids, like we have beryllium oxide, okay, silicon oxide, arsenic oxide, and antimony, these all are amphoteric in nature. Okay, keep in your mind that all the oxides of metalloids are amphoteric in nature. They have a tendency to show acidic as well as basic character. Okay, basic character, they, when they have a tendency to react with both acid as well as base. Okay, so you have to keep in your mind this thing also, that boron, if we talk about boron, so they have a tendency to show acidic as well as basic nature. Okay, so this is boron, not beryllium. Okay, I think I have already uh, taken it as boron, beryllium instead of boron. Okay, so this is boron, not beryllium. Now let's move on to their nature. The nature of the first element of each group is different from that of the rest of the groups. So what is the reason behind this? The main reason is that first reason is their small size. Okay, like in case of S block elements, we have lithium and beryllium. So they have a anomalous behavior. Uh, they have an anomalous behavior. Similarly, these all first elements have a some different behavior because of their small size, their electronegativity value, their ionization energy value. Okay, that is there is a large difference between these values. And the most important thing is they don't have vacant d orbital. Okay, write it in your notebook that they don't have vacant d orbital. That is why their covalency is limited. Okay, they will not show covalency above 4. Okay, like in case of nitrogen, so nitrogen is not able to form, like if we talk about phosphorus, so phosphorus can easily form pf5, but nitrogen is not able to form pf5. Okay, nitrogen can easily form nh4 positive only, which in as a cation only. Okay, so they have a covalency, maximum covalency of 4. Okay, they don't show not able to show covalency above 4. Okay, so this is the main difference. Due to this, they also don't have a tendency to form d pi p pi bonding. Okay, like in case of SO2, SO3, there are d pi p pi bonding present. Okay, as we move from lower member to higher member, the tendency to form d pi p pi bonding is more. Okay, d pi p pi bonding is not so effective because overlapping is very less. As we if we compare the overlapping between d orbital and this is our d orbital and this is our p orbital, so the overlapping is not so effective as in case of p and p. So p and p की overlapping थोड़ी ज़्यादा effective है as compared to d and p orbital. But due to this d pi p pi bonding, the coordination number increases. Okay, like in case of oxides, if we talk about oxides, so uh, nitrogen nitrogen is not able to form large oxides. Like in case of nitrogen is able to form NO2 negative, NO3 negative, but it is not able to form NO4 negative. Okay, but if you talk about phosphorus, so phosphorus is able to form PO4 3 negative. This is due to the formation of d pi p pi bonding. Okay, so the coordination number increases uh, due to this d pi p pi bonding in complexes also. Okay, but in case of these elements, they don't have a tendency to show this d pi p pi bonding due to the lack of d orbitals. Okay, so this is all about the general characteristics of p block elements. Now for plus one, we will start with group number 13. Okay, so there are only two groups in 11th class, and then in 12th class we will discuss about these four also. So in the next class we will start from group number 13. Okay, so that is boron family. We will discuss about their physical and chemical properties also. Okay, so this is all about the general characteristics of p block elements. Okay, and I hope you found this lecture very helpful. So thank you so much for watching the lecture.